Hello, everyone. My name is Yao-Yi Chiang. Thanks for the invitation to the UCGIS webinar. This is a after webinar recording. I hope that you will be able to watch this and share it with other people. All right. So today I'm going to present our project called Machine Reading Maps. I am an associate professor at the USC Spatial Sciences Institute, University of Southern California. I'm moving to the University of Minnesota, the Computer Science and Engineering Department in the fall. And this project is sponsored by, in the US, that's the National Endowment for the Humanities. In the UK, that's the Arts and Humanity Research Council. All right, so the problem. We're looking at historical maps. So why historical maps? I got these questions a lot. Existing data sources, they often only contain contemporary data set, right? Google Maps, GeoNames, OpenStreetMaps, they only have present place names. And maps, especially historical maps, they contain detailed geographic information at various times in the past. You have historical names, you have historical landscape, maybe there was a wetland, and now it disappeared. Tens of thousands of historical maps are just scan maps or scan images, and you don't really have any limited metadata. So make it very difficult to use them. So one example here of historical map use case, here you can see these are historical maps of Hong Kong. One of our USC GIS master students, they collected, she and a group of her friends, they collected a bunch of these maps and manually digitized them and create a very nice web dashboard here for land reclamation in Hong Kong. So you can scroll through time and look at how these lands change over time. But without metadata, how can we find relevant maps and make the map content useful? So before we talk about map content, I want to show you that finding relevant map is really difficult. Even when you know the time and region of your study area, it's often impossible to find them. Here is one example. This is a very, very nice project called the Yellow Star Houses project. In the project, the researchers identified almost 2,000 designated residents in Budapest. This is at the year 1944. Then they take all these addresses they found in the historical documents, they geocode them with the current geocoder. It's a Google Map geocoder, I believe. And they map it on Google Maps, which is very nice. If you look at the visualization here, you can see all these yellow houses. You will be able to do spatial analysis, see where are the hotspots and how they distribute over the space. However, if you overlay them on a contemporary data set like Google Maps, you lose the historical context or the geographical context of the time. For example, here shows you a historical map of that time. This is 1941, not exactly 1944, but it's close. You can see there are major transportation hubs, other types of street, other types of location names, street names, and open spaces. This gives you an idea, what was it like to live in that city at that time? But finding this map is not easy, so I recommend everybody to try this. You can try to see how long it would take you to find this large scale map, a very detailed map of 1941 Budapest. So how do people find maps today? This is one example from the British Library. So the British Library has made some of their map collections on Flickr. And the benefit of making map collections on Flickr is you can search by color, right? You say, I want some pinkish color, or I want some black and white maps. If you already know the map series that you are looking for, because different map series would have a very different color theme. You can also search by text. This is largely facilitated by our really advanced search engine these days. So Microsoft Bing, I take Microsoft Bing here as an example because Microsoft Research has a really nice paper on make maps searchable. I think it's published in ACM 6 Spatial a few years ago. But you can see you can search for Los Angeles maps, and it will show you all kinds of maps of Los Angeles. If we look at this Google example, also search image search, you can search by text. You say, I want to have Los Angeles historical maps or University of Southern California, USC historical maps. It will show you all kinds of maps. However, you would notice sometimes it doesn't really show you maps, right? And this is largely because all these search engines, they generate the metadata to facilitate the search by using the companion text of an image. So for example, if an image is on a website or this web text or a blog site, or this text can be something useful to provide an inverted index for the user to search. And the result is that you might be able to find relevant images, but they are not really maps. Another case is we can search by structured metadata. And this example is one map from the King's Topographical Collection from the British Library. And the collection has more than 40,000 items. It's a really interesting collection. I recommend everyone to take a look at them online. But you can see here, the British Library spent a lot of time and resources to create this type of metadata. It has a title, it has author, it has contributors, King George III. It has other information, tells you what are the geographic features included on this map. Right, so hundreds of towns, villages, parks, hills, and wood, and so on. But even with all this very expensive metadata, because you have to have some very good trained librarian to create all this metadata, and it takes time. But even if when we have this, when the maps are cataloged at the item level, we are still limited in the way that we can search for their content, right? So how do you search for this? Well, you can search for villages, but what kind of villages do you want? So that takes to our ultimate goal. I have been working on map processing since 2004. We have been looking for resources to help us fund this work. And our ultimate goal is to make the maps great again. By that, I mean, we want to be able to search maps very easily. And those searches or the infrastructure, the data infrastructure, the system infrastructure needs to be able to support complex queries. So complex queries like this. I want to find all maps from the 19th century UK that cover at least one church with 2 hospitals or clinics within a 5-mile radius, right? So this gives you some context of your study that you will be able to find the maps and use the map content to help you enrich your study. Also, we want to be able to convert map content to useful data that you can use in the spatial databases or in a geographic information system very easily to do analysis. And with as little user effort as possible, since we have too many historical maps. All right, so shameless promotion here. If you're interested in historical maps, in scientific studies and technologies that enable these historical maps in scientific studies, I highly recommend you to our book, Using Historical Maps in Scientific Studies from 2020. All right, in the Machine Reading Maps project. In the project, our goal is to create a generalizable machine learning pipeline that will be able to collaborate with human. So this is a very important part. We wanted to be able to work with humans for processing printed text on maps. So we are focusing on map text and enrich the printed text so that we can release tools and map data set to help our community who maybe museums or libraries who has lots of map collections, or researchers in the digital humanity or social science. They want to look at map content and use map content in their study, also to share data sets. So this project, we have the Alan Turing Institute from the UK, we have the University of Southern California in the US, and we do have the Austrian Institute of Technology. So these are the funded organizations. In addition to the funded organizations, we have our collaborators who are our advisory board. Their mission is to, it's mainly looking at our progress and give us ideas on how to push forward this line of research so that we will not build the tool that nobody's going to use, right? So we want the tool to be as useful as possible. We have the Library of Congress in the US, the British Library in the UK, National Library of Scotland, USC Library, the Penn State Library, and the Stanford Libraries. And we welcome everybody's input. So if you're interested or you have large collections of data set, you want to be a part of the project or a part of the advisory board, please feel free to send me an email. So why map tags? Why are we looking at map tags in this project? Map tags are extremely useful. Curators or librarian metadata librarians, they can use map tags to enrich collections or items metadata about the scope and features on a map. Then the researchers who wants to use maps can search for places and their generic types. So for example, a place could have a type park, right? Or a type residential area or a type clinic. So they can search for places and types of content and then use the data to analyze historical spatial information. So here shows you very detailed historical map. This one is, I don't remember the name of the collection, still don't remember, but in the US, this type of map is the Sanborn fire insurance maps. The Library of Congress has scanned them and put them online. In the UK, this is very similar, and you can see it has historical locations and business names, right? So this is Scottish Widows Life Assurance Office, tells you the street number, tells you the office boundary, tells you the length of this store front, and building materials, stairs, and many, many important information to tell you the geographic context of a location, right? How humans live in that environment. Another example is our past project sponsored by Terrago, also NEH, NGA, and CLS. So CLS is a title insurance company in the UK. They are the main sponsor of the project. So they want to look at, the problem is they want to look at all the historical ordnance survey maps in the UK and to identify potential contamination sites or to verify the history of a piece of land before they can issue the insurance. Right, so here shows you that in the historical map, 1920, you have quarries here, you have quarries here, right? In 1920, if you own a quarry, once you have some waste, what are you going to do? You're not going to recycle them. You're going to dump them in a nearby infill land. So that'll be here and here, right? So based on the map symbols and the labels, we know that all these three areas could be potential polluted area, right? Like here. So potential polluted area, and you still see some farming activity at present day, that might be a problem. Another use case is in biology. So what does map has to do, especially historical maps, with biology? A data record in the California Herbarium. So these are museum collections, and these are collections documenting observations of species. So this one says, in August 1902, someone observed a certain species near the location here, right? In the record, it says near Massmart in Los Angeles. However, if you search Google Maps or GeoNames OpenStreetMap, you cannot really find Massmart, right? There's no Massmart near or within both the boundary of city or county of Los Angeles. They no longer exist. So how do we find them? Well, I did Google it, and when I Google it, I find images like this. So it turns out these are commercial, it's a company called, they're developing a piece of land, and they call this new development Massmart City, right? They promise we're going to build a Massmart City, but the development eventually died down. There's no funding to develop it, so it disappeared. However, if you look at the USGS topographic map, you do have Mesmer here, right? Because it was a popular location name. People refer to that location Mesmer for years. So it's in a historical maps. So I hope I already convinced you map tags are important. Now I'm going to tell you what are the existing works and challenges in processing text in maps. So many existing approaches has been proposed and systems has been built to extract text labels from images, and some of them can handle maps. But a particular limitation that we saw is OCR tools or text label extraction tools can only extract separate words from map images instead of full location phrases. And these are not that useful. For example, OCR tools can extract fall and river, okay, fall and river, but not really fall river. It doesn't really know this fall and river needs to be put together as a location phrase. So separately, fall and river doesn't really carry much geographical meanings. So if automatic work didn't really get us there, how about crowdsourcing? So Recogito is a very popular online platform for collaborative document annotation, in particular for maps. And Recogito, by the way, is one of the component in our machine reading maps project. So in Recogito, a user will be able to upload their map, collect data, organize metadata of the maps, and this data could be text, images, tabular information, and you can collaborate with other people. So other people will be able to see the map you uploaded and help you with the annotation. Then you can export your data as open data. So on the right side shows you the Recogito current user interface. User can select a tilted box and start to annotate a text label and type in the name. Then click on OK to save the result, right? Very simple. But even when we have automatic or manual work to provide or extract text labels, we still need to have the geocoordinates of map images. There are existing pipelines for generating map metadata and georeference maps. But as you could imagine, it takes time. According to digital geography, the process for georeferencing one map, it's 10 minutes. And think about we have in the King's Topo collection, we have what, 40,000 maps, right? So this is a really long time. In our previous work, we worked with Google AI to develop a text-based method, use map text to automatically geolocate individual scan maps by using the single separate detected map words. And I'm going to show you this later as well. All right, so what's the current status of our MRM or machine reading maps project? So this is the overview of the entire project. On the left side, this is the input, and here this is the output. So let's look at the input. The input contains maps and their metadata. So the map can come from various sources, so various protocols to receive the maps, can be a WMTS tiles or a IIIF service. And the map can be in geotiffs if it's already georeferenced, or not georeferenced, it can be in TIFF, JPEG, or PNG. So from all these input maps, we have a processing pipeline going to Strabo. Strabo is our text detection and recognition tool for map images. And from Strabo, we will be able to automatically generate annotations, locations, and meanings of text labels. We will send it to Recogito for verification. So human will be able to look at the result, collect the result, and have the access to external knowledge base, could be Wikidata, OpenStreetMaps, or other gazetteer to help verify the annotation, automatic annotation result and link the data set. Also, the result from Strabo will be sent to Map Curator. So Map Curator is actually today's focus. I'm going to get into the details into Map Curators. In Map Curators, we can automatically predict labels. So that means we can link individual recognized words, Los Angeles together into Los Angeles, and we can link them to external data set to provide meaningful metadata or rich metadata for each phrase. And together, the output becomes gold standard data sets that everyone can use, and we can also use them to improve our machine learning tools in Strabo and in Map Curator. So one important thing after this summer, we plan to release our first version of the integrated Recogito, Strabo, and Map Curator so that the user will be able to use Recogito and with some semi-automatic way from Strabo and Map Curator to annotate historical maps very easily. So overall goal in MRM is to integrate machine learning technologies, which include, in this case, Strabo and Map Curator, with the proven online collaborative annotation platform, Recogito. So let's look at the latest Recogito development first. So first, we have some new annotation interface in Recogito. The first one is for arbitrary shape annotations. So the user can start to select arbitrary shape, polygons, and annotate an area, right? In this case, we want to annotate a building outline. The second one is to annotate linkages. So on the right side, you see the user annotate beacon, annotate street, and the user can say, all right, beacon and street should be linked together. So this is a location phrase, beacon street. In addition, in Recogito, we are working on this semi-automatic annotation interface. So this is very similar to the concept of integrating Recogito with Strabo and Map Curator, that in this case, the user wants to digitize the boundary of a parcel. So the user only have to select a bounding box, and the machine learning algorithm will automatically narrow down the bounding box, find the boundaries of a parcel, and ask you to provide a label. Okay, so this, we hope, will be able to significantly reduce the amount of user effort in digitizing map content. The last component in Recogito is to integrate place entities and image annotations, because all the annotations that you have seen so far in Recogito still exist in the image domain. That means your annotations are image coordinates. But in Recogito, we do have this functionality to say, hey, if you label this location and you say this is York, you can select and you can search, select, and link them to, like here, this is geoname entity York, right? So in this way, all the map locations on maps has a link to an external knowledge base and make them even more searchable and support complex queries. Also, we follow many different standards. We support linked data format. We are going to use common vocabularies like Wikidata. In annotation, we use a web annotation data model, and we use JSON LD. So again, this is the summary of the entire MRM project, and today's focus is on Map Curator. And everything developed under this project is open source. All right, Map Curator. So the goal for Map Curator is to generate linked historical maps with semantic rich metadata. And this work is a collaboration between the University of Southern California. Zhe-Kun Lee is my PhD student. She's leading this work. Google AI, and this is USC Information Sciences Institute. And we also have people from the University of Colorado Boulder Geography Department. And the paper was published in KDD 2020. All right, so generating semantic rich metadata. What are the challenges? Existing map processing pipelines, they usually only extract partial metadata from map images, or they're not very efficient. So also the map data extraction process involves manual steps for geolocalization, right? So image coordinates are not good. We really need to know what are the Earth location of each of the map tags. The information obtained from automatic methods like optical character recognition is often not complete. So OCR tools cannot provide us the linkage information between two words like Los Angeles versus what we really want is Los Angeles. Extracted single words are not really associated with any additional information. It doesn't have location. It doesn't have a type like Los Angeles. Is it a city? Is it name of a street? What is it? So Map Curator has a number of contributions. First, it's a machine learning model. It contains a machine learning model to predict the linkage relation between words so that we can put individual words together to generate location phrases like Los Angeles. And given a set of location phrases, we have a clustering-based geolocalization method. We will be able to infer the map center, right? So that's the geolocalization part. And together, it's an end-to-end pipeline for automatically metadata extraction and linking for historical map images. The output are location names contained in the map, geolocation of the map region, and links from all this map content to external knowledge base. So input of our method. Let's look at text labels in contemporary and historical maps. This, I believe, is London. And on the left side, you have Google Maps. On the right side, you have the Ordnance Survey maps. So text labels can help us understand the underlying geographic features inside the map images, right? We'll be able to know if this is a street or building or something else. Within our context, there are two types of labels in the historical maps. The first type, they appear in both historical and contemporary maps, like this one. You have a street name here. You also have a street name here. Okay, so that means the street doesn't really change name over the years. Or you have square, you have a square. Great. The second type is the names that only appear in historical maps, like Riverside here, Derbyshire, House, Sandfield. So all this information, these are historical names. They might disappear in already, so the current data set do not contain them. So in this work, we are going to focus on the first type of the label, the one that exists both in the contemporary map and the historical map. And we're going to show you how we use them to generate rich metadata from historical maps. But in general, in the MRM project, we are also interested in the historical names, and that's our ongoing work. All right, Map Curator overview. The input of Map Curator is a map image. Then the first component is called the location phrase generation. We're going to extract location phrases like Mindago Creek, La Honda, Skyline Ridge, and so on. Then the second component, map geolocalization, we're going to take all these location phrases here and use them to geolocalize the map image. So now we can put it on top of a georeferenced image or map. Then we are going to take the map content, match it to an external knowledge base. In our case, we use link geodata. So once we can link them, we will be able to generate link historical maps. And this is a fully automatic pipeline with very rich metadata. So I'm going to show you these three components one by one. First component, location phrase extraction. Since this is a collaboration between us, USC and Google AI, we do have unlimited resource to use Google Cloud. But if you want to do the same thing, you don't have the resource to do Google Cloud, you can use our tool. our tool for text detection and recognition will be released after summer this year, 2021. All right, Google Cloud Vision API gives us something like this. So it says, well, scan historical maps as input. Google Vision API says, here's a Mindego, here is a hill on the map, and tell you the location of these words on the map. Our goal is to be able to predict if these two words needs to be linked together as a location phrase, Mindego here. So our first machine learning model in Map Curator is a textual model. So textual model is based on the idea that labels in the same phrase should share similar textual content or textual features. By textual features, we say, all right, your capitalization must be similar, font size must be similar, angle must be similar, or along a line or a curve. Location must be nearby. Word embedding must be similar. So by word embedding, if you're not familiar with word embedding, it's a natural language processing tool that will be able to convert each word into a feature vector, a set of numbers. And then if your two sets of numbers are close, that means these two words are semantically close. All right, so take all this information of the label, the recognized label here, Mindego, and here we train a classifier using triplet loss. This means that we will give the machine a few examples. We say, all right, Mindego and Hill should be linked together, but Hill should not link with endless, or Hill should not link with loss. So this model gives us really high recall. That means if two words should be connected, we will most likely say they should be connected. But low precision, that means we have a large number of false positives. Many times when we say we need to connect them, you don't need to connect them. So to improve this model, we have a second model in Map Curator. It's called the visual model. This model is very cool. It's based on the concept or the idea that labels in the same phrase should have similar nearby geographic features, right? If the words are, if the phrase is describing river, Los Angeles River, they should all be nearby the river on the map. So their visual appearance would be similar. And you can see during training time, we have a map and we have the masking this word. And after we mask this word, this is a supervised learning. So we also say, okay, so these two parts should be linked to your masked words. And we adopted a unit semantic segmentation model to help us to do this prediction. And this visual model works very well. It has low recall, but very high precision. So it helps us to correct this low precision part, right? Because right now we can just use the textual model to generate candidate, then use the visual model with high precision to help us refine the candidates. So high precision means if you say these two should be linked, there's very high chance they should be linked. So the output looks like this, Mindego and Hill. Now we know they should be linked in the same phrase. So this is the location phrase extraction component. The next component is map geolocalization. So the input of this component is the location phrases generated from the last component, right? Mindego Creek, Skyline Ridge, La Honda, and so on. Then we take all these location phrases. We use a geocoder. Again, here we use Google Geocoder. If you don't have access to Google Geocoder, you can use a free geocoder, text A&M, still serve one. Geocoder will give us a list of candidate coordinates for each names because Mindego Creek might exist in many places, right? So in this example, we have two Mindego Creeks at different locations. So to be able to use this and identify which one is the real Mindego Creek, we do a clustering. We apply a DB scan on the entire candidate sets. And in this case here, you can see we have 4 colors. So we identified 4 clusters and we say the largest cluster, because this should be most of the map label candidates agree, and this would be the map content location, right? It should represent the map. So we use the centroid of the largest cluster as the map geolocalization result. So now we are done with the geolocalization. The next component is entity linking. So in entity linking, now remember we have georeferenced all the location phrases. We have Mindago Creek, again, all the names, but now we have their geolocation. So the entity linking component is very simple. We just match name and location of the location phrase to an external database. In our case, we use link geodata. And you can see if we can find a match. Now each of these nodes are in the link geodata. It gives us lots of information like elevation, county ID, name again, and the classification of the feature. This one is a peak, and so on. So this way, after the linking, Mindago Creek on the map is linked to an OSM node with all kinds of extra metadata. It's not just a string anymore. So with all these three components, we have conducted a comprehensive experiment. So in our experiment, we tested our approach to evaluate the location phrase extraction and evaluate the map geolocalization component. Our data sets include the USGS historical maps with more than 4,000 text regions. We manually create them. Thanks for all the students who contribute to creating all these text regions. So this maps has ground truth for geolocalization and location phrases. We also tested on ordnance survey maps here. So this is the USGS map. This is just one sample. We have 15 maps. For the ordnance survey maps, we tested on 10 maps with more than 2,000 text regions. They have ground truth for phrase generation. We didn't get the location of each ordnance survey maps. The last set of maps are the New York Public Library map collection, historical map collection. We have 500 maps. They do not have text region annotation, but they do contain ground truth for geolocalization. All right, for location phrase extraction, we tested that only use the textual information for linkage prediction and use the both visual and textual model. So you can see by using both visual and textual model, our F1 score is pretty good. Precision is pretty good as well for all the tested map. Recall was okay for USGS maps. It's about 60%. Sometimes you have 33%. So this is because if the texts are too crowded, we cannot really get, we cannot really obtain the OCR text, not alone to predict the phrases. So we are working on improving text detection and recognition result. We will release the tool with Recogito after the summer. The second experiment is for geolocalization. In the experiment setting, we tested 3 types of geolocalization systems. The first one is our baseline. This is a Google AI system. They would just do OCR on the map and put all the words together into one paragraph, feed the paragraph to a geocoder, and hope the geocoder would be able to figure out the location. The second approach is a variation of map curator. Here we feed each word into the geocoder, and then we do this clustering method. The third method is our map curator. This is our real map curator. This is used generating all these phrases from words. So no words anymore, phrases. And with the phrase, we feed the phrase into geocoder followed by a clustering method, like what I just showed you for the 3 components. So before we look at the result, let's understand how we differentiate the result. So here is one example, second example. For the example on the left side, you have the baseline approach. This is the Google AI approach. This is the map true location, and the baseline approach says it's here, right? So it's far away. And word by word approach, the variant of map curator gives you here, phrase by phrase, the map curator gives you here. On the right side, here the baseline approach, Google AI's approach did not generate a location. It couldn't find it. And for the word by word, it's here. And phrase by phrase is here. So I want to say this is very important. Oh, if you don't know, this area is Los Angeles. So this gives you the scale of the map. So it's important that the identified geolocalization result, although not perfect, it should be within the map region. So that the goal would be we automatically guess an approximate location of the map, and the user will be able to move the map around that area to find the precise location, right? So again, as here, if your location is close, the user will be able to find it. If you're far away like here, it will be difficult for the user to know, right? If you place the map here, it will be difficult for the user to know the map is actually placed here. In contrast, if you place the map here, like in our approach, there are some overlapping content. So the user would be able to guess or to automatically, to manually correct the result. All right, geolocalization result. Geocoding using alt text, right? This is Google AI method. This is word by word method. And this is map curator. One thing that's really cool I want you to look at here is for all these maps, map curator result put them all within the map content. So this is not map scale, this is the accuracy scale. So if this is less than one, that means the map image actually covers the predicted geo coordinates. So for word by word, two of them are still within the content. This one is not. Google AI's baseline, these two are not. This one is within the map content. So for geolocalization using 500 maps, this is the result. On the x-axis, these are the errors. So here are the no result, and here are the positional offset between the predicted location and the ground truth. Yellow one is map curator, and again, red one is our variation, word by word, and blue one is the Google AI baseline. So from here, we can see Google AI's baseline has many of the maps have large errors, right? And also they have many of the test maps has no result. Map curator and its variation has fewer maps without result. Also, map curator and its variation has smaller errors compared to Google AI. So you can see pretty long bars. So these are number of maps, right? So here it's about 200 maps are within 1 to 5 kilometers between the predicted location and the ground truth location. For entity matching, here is to show you one example result. Once we match the words location phrase to an external database, we'll be able to generate something like this. And here we are leveraging an existing ontology. This ontology is from our other paper in ESWC about modeling and linking historical maps and current knowledge base. All right, so here you see node. This node is has a link to a map image, and based on this ontology, you can start to see, all right, this node is a type of map, and it's nearby some WKT location, overlaps with some feature. This feature has some WKT, well-known text location, it's a geometry. And this feature has a label. This label is Black Mountain. And what's really nice is it has a link. So see also, if you want to know more about this feature, you can see this link. And this link is at the link geodata gives you all kinds of attributes about Black Mountains. So what this can do is we enable this type of queries. So this is a Sparkle query. Even if you don't know Sparkle, this is pretty easy to read. It says we have a few prefix namespaces that you can find external sources. We want to find maps where in this maps has to overlap with something. It has to overlap with features in link geodata and with geonames as elevation. Okay, sorry, geoname elevation has an elevation higher than 1,000 meters, right? So this is the same as asking search for maps that contain mountains higher than 1,000 meters. Now you can search for historical maps, just writing this very simple Sparkle query. So, all right, so in discussion, I show you Map Curator is a fully automatic pipeline to generate semantically rich metadata linked to external knowledge base. Map Curator can generate location names containing the map, geolocation of the map region, and links from the map content to external knowledge bases. Map Curator combines both visual and textual information to significantly improve location phrase generation. Now we know Los Angeles should be Los Angeles. This Map Curator's pipeline outperform geolocalization pipeline, outperform all the baseline models. And in our ongoing work, not just future work, ongoing work, we're working on this. We want to do semantic typing for map tags that are not in the knowledge base, right? All these historical names, we cannot really find a counterpart in contemporary data set, but we could still use the neighborhood, geographic features, and maybe the time of that map to help us reason if, does this place name mean a park, or it's a residential area, or what is it in the historical map? So other ongoing map processing work in our lab, we have object detection from geoimages, including historical maps, using limited training data. We do not like manually creating training data. So here you can see a map. Our goal is to extract the wetland symbols, and we only have these blue boundaries. This is from OpenStreetMap, giving you the current boundary of the wetland area. It's not accurate, right? So we want to be able to use the map symbols to refine this boundary. So our work takes the boundary and one or two wetland symbol example, and we were able to identify all these locations of symbols and refine the boundaries. We just submitted this paper to a vision conference. The second part, other ongoing map work. This one's very, very cool. So it's called encoding the words geospatial data. If you look at this, here are 4 images. And in these 4 images, you can see, I didn't tell you they're the same, they cover the same area, but you can see, right? So some notable building here and major roads, right? All these features, you know, and this one as well, and this one as well. So we are building a representation learning method that will be able to help us get this hidden information out. So eventually you just give the model a map image, it will be able to tell you the location, maybe the location of the image, and any other important geospatial property of that location. All right, so just a recap of our machine reading maps project. After this summer, we are going to release a first integration of this. And I hope you will try this release and let us know your feedback. And if you want to join the advisory board, please send me an email. So acknowledgement, the MRM project, in the UK, we have Kathy McDonald, Valerie Vitali. In the US, we have me, Spatial Computing Lab USC. We have Zai-Kun Lee, Deb Holmes Wong. Austria, we have Rainer Simon, who is mainly in charge of developing Rekajito. He is the person behind Rekajito. He has been working on this for many, many years. All right, here's our advisory board, and we thank them very much in sharing data sets, tell us about their challenges, difficulties, working with us to solve all these challenges. We love maps. I love maps. So if you have any comments, feel free to send me an email or come to our website. The project is still new, so there's nothing much to see on our MRM website, but if you send me an email, I will keep you posted once we release the tool. All right, thank you, everybody. I hope you find this interesting, and I hope you find the tool useful. If you do, please don't hesitate to let me know. Thank you.